Okay. Circular motion. Okay, so let's just do a little recall here first. Recall this. Newton's first law is the law of inertia. Okay? And that's just this. Mass requires force to change its motion. Okay? That's it. More mass there is, more force you need to get it to do what you want, to change how it's behaving. Okay? So here's a couple of just basic examples of this. What are we here? I want this. Okay, so, let's say you have a massive object like a ball, and it is zipping along in this direction. We understand that basically this object will continue to roll forever, really, until or unless a force acts to slow it down, right? And if we apply a force in the same direction that it's moving, it will speed up, okay? So far, so good. No one has a problem with that. And if we want to actually apply numbers to how that works, well, that's where Newton's second law comes in, just F equals ma, right? If this is m, we can figure out the acceleration of the object based on the force applied to it. We've been through that. No problem, no question, we're all good. And by the way, Newton's third law just basically says, in order to apply a force, we got to touch something, right? So if we're touching it, it's applying a force back on us. Really, that's the basics of physics in a nutshell. Everything else just stems from this, right? So we call that action-reaction. Now, when we're talking about circular motion, we don't want to change the motion of this object in the same plane that it's moving. Now what we want to do is we want to deviate it from its inertial path along a circular path, right? Like this. So if I take this object and we think about what we're going to have to do in order to make that happen, okay? If it's natural tendency, why did that change color? I don't get it. And direction. Its natural tendency is to travel along like this, okay? But we want to get it to follow a path like this, right? We want to get it to move in a circle. It should stand to reason that we're going to need to apply a force in this direction, right? If you think about a bowling ball rolling by and you want to make it turn, you're going to have to push it in the direction you want it to turn. Does that make sense? And you're going to have to keep doing that, right? Because the second, so what we might do here is let's put a string on this thing, right? And let's put a stake into the ground and let's give it a high velocity. Well, inertially, it tends to move in a straight line in the direction it's currently traveling. That's just the way inertia works, right? Now, what we're clearly doing here is we're applying a force on the object in this direction, right? At this point in time. Sometime later, let's put a few more of these around the old circle. Okay, so this is the path it's following, a circular path. And this string's really ugly, so I'm going to fix it. We've strapped a string on. It doesn't necessarily have to be a string. That's one way to make this follow a curved path. We'll talk about other ways in a minute. But we've got that. Okay, applying a force towards the center at that point. And here's our string. We still have it, right? Still have it. If we look at any one of these points, okay, try to make this look okay. Okay, sort of looks okay. At any one of these points, we can see that the applied force is towards the center there. Come on, arrow. towards the center there, towards the center there, and so on. In your mind, you can imagine this. I must apply a constant force towards the center, or this object will continue off in a straight path. So let's imagine at this point, we cut this rope, right? We put a scissor on it. We just snip it. Rope cut. What happens to this object the second I cut that rope? Does it fly off like this? Heck no. Why? Because we got to think in terms of Newton's laws. Its velocity at this point has now been converted to being in this direction. Right? That's its new velocity at this point. So what's it going to do if I cut the rope? It's going to fly off in the straight line just following its inertial path. If you've ever seen someone use a sling, you know, one of these things to whip rocks, like, you know, they whip it around in a circle real fast and then let it go, okay? Well, when they want it to go straight ahead, they let it go when it's at 90 degrees to the right, because then the velocity of the rock is in the direction they want, and inertia will carry that object off in the direction we want it to go. So what we're interested in is this force, okay? It can be applied using the tension in a rope, right? But it can be applied in many other ways. How else could I get an object to move in a circular path? What if I built like a little wall that happened to be curved? Would that wall provide a force towards the center? Sure it would. Okay, so this could follow the curve of a wall, right? Let's say there's no rope, but let's say that this is positively charged. And there's something negatively charged in the center, or better yet, make this negative and make this positive, and then we might have electrons going around the center of an atom, okay? Whether that's fair to say or not, we won't go there, okay? Or we could say that these are masses, and this is outer space, and this is a big mass, and these are little masses, and we would have an orbital system, right? Where an object continues in a path this way. Now, something interesting that happens here. When we looked over here and we applied a force to a mass, that caused an acceleration and thereby changed the magnitude of the velocity of the object, right? We push something in the direction that its velocity is going in, it either speeds up or slows down. If it's rolling towards me and I push it, it's going to slow down. If it's rolling away from me and I push it away, it's going to speed up away from me, right? In this case, we are applying the force at a right angle to velocity. At a right angle to velocity. So what that means is that this force that we have here will not affect the size of the velocity. Size stays constant. Okay? So how, if you want fast this is going, does not change. The speed does not change. But we're applying force. And we know forces cause accelerations, right? So what does that mean about this object? Is it accelerating? The answer is yes, it is. If I'm applying a constant force to something, yes, it is accelerating. However, it's not accelerating by changing the magnitude of the velocity. It's changing the other part of the vector of velocity. Remember, vectors have what? Magnitude and direction. So we are causing acceleration, but not affecting the magnitude, affecting the direction. So Newton's laws are still obeyed, okay? The velocity is changing, just not the size of it. The direction of it is constantly changing. If you think about that, every split second, this velocity changes direction. And it's always, always, always tangent to the curved line. Velocity is tangent to circular path. Okay? So there's a whole bunch of stuff. Is any of that outside of your previous experience or outside of your common sense? Is anyone having any problems digesting where we've gotten so far? All right, so let's derive. Drive to 7-Eleven and get me a Slurpee. All right, so. Okay, well, let's get this thing here, and let's put it here. So we're going to look at this circular path here, and we're going to start by putting something in the center of it. It's roughly the center, okay? And let's say that we have an object that is moving around the circle. At one point it's here, and at some point later it's here, okay? We'll draw in some velocity vectors. So we've got one there, and we've got one there. Actually, I want to use the same one because we're going to use these. Let's see here. Make this bigger. We'll copy it. Make another one. I don't know if I can swing. Ooh. No, that doesn't let me do what I need to do. Whatever. I'm not overly concerned, okay? It's got to be roughly the same length. There's probably a way to do that, but that's close enough. So this is an object meant to be represented here as moving around this circle, okay? And, oh dear. And we've got, we'll say something, come on, man. We've got, struggling here. We've got a connection to the center here and here, okay? So we're going to call this point A. We're going to call this point B. And we're going to say that this is some angle theta. And we're going to say that this takes some time to do, right? Which would make sense. To move from here to here is going to take some time, okay? And we're going to call this V1. We're going to call this V2. And we're also going to say that there's a distance here, right? There's a distance covered in some amount of time. And so we could also say d equals velocity, and that's the magnitude of velocity times the time. Okay, so we know that as well. Pause for a second. All right. So now, we said before there's a force acting towards the center, right? There's a force acting towards the center. And that force has a name. Okay? The name is the center-seeking force. But saying center-seeking force all the time is a giant pain. So there's a word, I think from Latin or possibly Greek, I don't know, called centripetal, which just means center-seeking. Okay? A center-seeking force. Okay? People will often say something like centrifugal force. Okay, there's no such thing as centrifugal force. Well, there kind of is, but it's not what people think it is, okay? So I'm going to give you a quick example. Let's say this represents your car, okay, driving to the right. Are you with me? And let's say, imagine you're in your car, staring out the windshield, and there's like a quarter sitting on the dash. Are you with me? This is the quarter that is sitting on the dash of your car. Okay? Now let's imagine your car's following this path. Okay? Think about the quarter. Does it have mass? If you turn, right, everything that is attached to your car, such as you're seatbelted in, okay, the gear shift, the steering wheel, the seats, everything, follows this path. Well, what's holding the quarter and making it turn, right? The friction between the tires and the road makes your car turn, but there's much less friction between a quarter and your dash. So what you would observe is, as you turn, that quarter tends to follow its path continuously, right? It's got inertia in the forward direction. So if I'm driving along the road right here and I suddenly decide to go around this curve, the center-seeking force is provided by friction between my tires and the road, but only the friction between the dash and the quarter can make it turn. So if I whip my wheel real fast, it's going to seem like that quarter shoots to the outside of my car, right? I'm just turning away from under the quarter. It's following its straight path. If you could suddenly make your car invisible of everything except the quarter, what you would see is just a quarter moving along and following its straight path. But from the observers inside the car, they're getting actually turned away from the straight path of the quarter. Eventually the quarter comes against the, side wall of the dash or whatever, and it gets turned too. Okay? You feel this in yourself, in your upper body, when someone whips a car because they're driving like an idiot. You seem to get thrown to the outside door. What's really happening is the car's turning. You are continuing on your straight path. Okay? All right. So quickly. What we're going to say here is, if I want to know the change in velocity, If I want to know the change in velocity here, right? Well, what I got to do is I got to take V2 subtract V1. V2 subtract V1. So I want delta V, the change here, right? Because the change in velocity is going to be equal to the acceleration, right? The change in velocity over the time this takes is going to be equal to my acceleration, except that we're not dealing with magnitude anymore, we're dealing with direction. So I've got two vectors here that I got to deal with. I got to take that guy, which is V1, and this guy, which is V2, and I got to say V2 is going to subtract V1. Well, we remember that vectors are added tip to tail, and when we subtract vectors, we add the opposite vector. So V2, which is this, subtract V1 is actually adding the flip. Like that. Okay? And what we end up with is a new vector, which you will see here is actually going to point towards the center of the circle. So there's our new vector. And what we're going to say is, well, this is the acceleration, right? This happens over a time. This is our centripetal acceleration. Okay? And what we're also going to say here is that theta and this theta end up being similar to each other. We're also going to say that if we make a chord across here, okay, if we make a chord across here, and then we decrease this angle, what we'll say is that chord AB approaches the same length as arc AB, right? As this gets smaller, the chord and the arc become the same, essentially. All right? So this distance across here is the equivalent, if you want, of this chord over a small enough angle. Kind of calculusing a little bit. Okay? And so what you get then is you get that, so this is delta V, right? And that is the equivalent of chord AB. So we'll say that. Delta V on the similar triangle is chord AB. Okay, and this is, what we say, this was V1 and this is V2. And this is the radius, right? There's the radius of this circle. Are you with me? So then the ratio of V1 to delta V, or any of these V's, are the same size in terms of their magnitude, should be the same as chord AB over R. Okay? And then what we're going to say is, we're going to decrease this to a point where this is actually going to be equal to displacement, right? Displacement here is the velocity times the time, right? This is true because we're saying the angle is small enough that this displacement across here is the same as the chord, all right? So then we're going to sub that in, and we're going to say this. Delta V over V is equal to V delta T over R. All right, and then we're going to do some more math. We're going to multiply this and bring it up here. So delta V over V, nope, I don't want to do that. Delta V equals V delta T over R, or we get delta V equals V squared delta T over r. We're going to divide delta t off of this side, so we get this. Delta v over delta t equals v squared over r. And delta v over delta t is our centripetal acceleration. And we did it. Okay, so here's our formula for the centripetal acceleration. All right, now we want to know, how do we get the centripetal force? Well, F equals MAC. So we're just going to do that. Multiply both sides by the mass. MAC equals mv squared over r. This is a force. We call that FC equals mv squared over r. And there we go. We've got a brand new centripetal force formula. Just in time.